Hi, hello students, good evening everyone. I hope all are doing well. Anyway, welcome back all of you to Infinity Learn JEE YouTube channel by Sri Chaitanya. This is Miss Surya, your chemistry faculty from Infinity Learn. Okay, if anyone is watching this particular live, please give me a hi. And I hope I am perfectly audible and visible to each and everyone present over here to watch this particular session. So finally, we are moving to the last part of our chapter, hydrocarbons, that is about the aromatic hydrocarbons and their properties. So let's start with the first topic. Okay, let's start about the physical properties of aromatic hydrocarbons. In the last class, we have already discussed about all the isomerism, IUPAC nomenclature and the properties of aromatic compounds, right? Starting from the aromaticity, non-aromaticity and anti-aromaticity. Here we are going to discuss from the physical properties of aromatic compounds. Then we are finally moving to the chemical properties also. So we can start with the physical properties here. As you can see over here, all the aromatic hydrocarbons are generally colorless liquids, right? They are colorless liquids or solids having a characteristic smell, because of them known as aromatic compounds. The aroma means they have a pleasant smell or pleasant odor, right? So for example, if you are taking naphthalene balls, I hope everyone familiar with mothballs or naphthalene balls, right? So which is used for the preservation in toilets, right? Preservation of clothes and which is used in the toilets is known as a naphthalene balls, which has a characteristic smell and as an repellent property for insects, right? This is an example of aromatic hydrocarbons, which means that they are colorless liquids and solids having a perfect smell, right? Clear? The second physical property of aromatic hydrocarbon is about their solubility, right? When you are talking about the aromatic hydrocarbons, the first compound that comes in your mind is our benzene, right? So here in the case of benzene, they are generally insoluble in water, but they are soluble in polar solvents, right? Or organic solvents. Clear? So this is about the physical properties of aromatic compounds. You need to mention that all the aromatic hydrocarbons are colorless solids or liquids having a pleasant smell, and they are highly insoluble in water, but they are soluble in organic solvents. Now let us talk about the chemical properties of aromatic compounds, right? There are few more examples, reactions are given here, as you can see over here. In particular, we need to talk about electrophilic substitution reactions. Among them, we need to focus on nitration, sulfonation, halogenation, Friedel-Crafts alkylation and acylation, right? We need to focus on each reaction separately in your examination point of view. Then after that, we need to focus on the addition reactions and combustion reaction. Ready? So let's start with the first reaction. Yes, our nitration, right? What do you mean by electrophile? The compound which is loving electrons, right? Electrophile means the compound which loves electrons are known as electrophiles. In general, in the case of electrophilic substitution reactions, in the case of aromatic hydrocarbons, we need to focus on the first reaction, that is nitration. As the name itself suggests that a nitrogen group is adding, right? NO2 group is adding here. So for example, if you are taking benzene as the reagent here, benzene, right? This is our compound. It will reacting with nitrating mixture, which means the mixture of HNO3 and H2SO4. The mixture of nitric acid and sulfuric acid is known as nitrating mixture. At a temperature of less than 60 degrees centigrade or degrees Celsius, you will get a product like that. In the case of a benzene ring, an NO2 group is introducing rare, right? So this is the general reaction for the nitration reaction for aromatic hydrocarbons, particularly for benzene. Okay, I hope it is clear for everyone. Now let me move to the next type of reaction. That is our sulfonation, right? Sulfonation. As the name itself suggests that sulfonating group is adding to the benzene ring, right? SO3H group is adding to the benzene ring by using sulfuric acid as a reactant, right? Fuming sulfuric acid, which means that sulfuric acid in presence of SO3 is known as a fuming sulfuric acid. If our reactant benzene is reacting with fuming sulfuric acid at a temperature of 100 degrees centigrade, it will produce a product like this, in which SO3H group, sulfonic acid group, is introduced into the benzene form. Benzene sulfonic acid, right? This is our reaction of sulfonation. What you are observing here, when you are treating with any of the reagent with the benzene, it get attacked there, right? You will get a product like this. So this is the second type of reaction, second type of electrophilic substitution reaction. So as you can see over here, this SO3H group, right? SO3H group or NO2 group is act as an electrophile in these particular reactions. Clear? The next type of reaction is the halogenation. What do you mean by halogenation? Halogen is adding, right? So if you are taking any of the halogens like chlorine, bromine, iodine or fluorine, right? So we can say that benzene generally reacts with chlorine or bromine in presence of Lewis acids. I hope already must have an idea about Lewis acids and bases here. So here the Lewis acid uses are either anhydrous FeCl3 or FeBr3 or aluminum chloride AlCl3, right? These are the common Lewis acids which is used for the reactions for halogenation here, right? What you are observing here, which product is forming here? In general, if you are taking benzene, right? This is our benzene. I am adding chlorine, Cl2 molecule in presence of anhydrous AlCl3. What will be the product observing here? If I am adding chlorine molecule in the presence of anhydrous AlCl3 to the benzene molecule, what will be the product are you expecting? In one of the position, the hydrogen atom is substituted by chlorine atom, right? So here you can say that this will be our product, that is chlorobenzene. Right? So what about the next reaction given here? Do you have any idea about this reaction? This first reaction is a general reaction for the halogenation. For example, if you are adding chlorine, bromine or any of the halogens in presence of anhydrous aluminum chloride, you will get a product like this, in which one of the hydrogen atom is substituted by the chlorine, bromine or any of the halogen we are using, right? For example, here you can observe I am taking only one chlorine atom, right? One chlorine molecule. Here I am taking only one chlorine molecule. Instead of this, if you have taken second reaction, right? This is our second reaction. What you are observing here, I am adding 6 molecules of Cl2, right? 6 molecules of Cl2. Which means that I am adding excess of reagent here, excess of chlorine, right? Excess of reagent here. If you are adding excess of reagent here in the case of halogenation, you will get a product like this. What is the product here? 6Cl2, right? In which means all the hydrogen atom which is present in the benzene atom get substituted by the chlorine atoms to form hexachlorobenzene, C6Cl6 molecule by releasing 6 molecules of HCl. Clear? Similarly, instead of using chlorine, you will get the product like this, bromine. If you are taking bromine in presence of anhydrous AlCl3 or FeBr3 or FeCl3, you will get the product like this. Instead of chlorine, it will be bromobenzene. Clear? Now let me move to the next type of reaction, that is our Friedel-Crafts alkylation, right? Friedel-Crafts alkylation, which means that we are adding an alkyl group to the benzene, right? Alkyl group to the benzene. The reaction going on here, if I am taking benzene, right? This is our benzene. If I am treating with alkyl halide, this is our RX molecule, which means alkyl halide, right? In presence of anhydrous aluminum chloride, right? This is our Lewis acid here. What you are observing? This alkyl group gets substituted here to the benzene to form alkyl benzene, right? Alkyl benzene. For example, if I am taking methyl chloride, right? This is our methyl chloride. If I am adding methyl chloride in presence of anhydrous AlCl3 to the benzene, what I am observing, what is the product I am getting? Toluene molecule, right? CH3 group gets attached to the benzene to form toluene molecule, right? Clear? And similarly, if you are taking ethyl bromide, right? This is our ethyl bromide. What will be the product? If you are taking any of the alkyl halide, alkyl group get attached to the benzene to form corresponding alkyl benzene, right? So here C2H5Br, in which C2H5, our ethyl molecule, get attached to the benzene to form ethyl benzene, right? Ethyl benzene. This is our product forming here. Clear? So here we are adding alkyl group, so the name given like this, alkylation. The next reaction we are going to discuss is the acylation. What is the difference between alkylation and acylation? In the case of alkylation, an alkyl group is get attached to the benzene group. Here in this case of acylation, you can see that an acyl group, right? This is our acyl group. This is our acyl halide, right? Acyl chloride. Okay. In words, we can say that the reaction of benzene with acyl halide, acid halide, or acid anhydride in presence of Lewis acids such as anhydrous AlCl3 to form acyl benzene is known as the Friedel-Crafts acylation, right? So here in this case of Friedel-Crafts acylation reaction, an acyl group is get introduced into the benzene group to form corresponding acyl benzene, right? Here this is a general reaction. If you are taking CH3COCl, right? What you are observing here, CH3COCl is get attached to the benzene to form an acyl group is attaching, right? COCH3, which compound it is? COCH3 group is attached to the benzene ring, right? So in the next reaction, what you are observing, similarly, instead of acyl chloride, right? Instead of acyl chloride, we are adding acid anhydride, right? Acid anhydride in presence of anhydrous AlCl3 to form similar product, right? Similar product, in which CH3COH, acetic acid, is taken as the byproduct here, but in the case of here, it will be HCl as the byproduct. That is the only difference between these two reactions. The main thing you have to keep in mind that instead of Friedel-Crafts alkylation reaction, in the case of acylation reaction, we are adding acyl halide, right? Acyl halide or acetic anhydride or acid anhydride to produce the corresponding acyl benzene. Clear? So far we have discussed about the type of electrophilic substitution reactions, right? We are starting from the halogenation, nitration, sulfonation, Friedel-Crafts alkylation and Friedel-Crafts acylation. We need to do the mechanism for this particular reaction, right? In order to get which product is getting as the major product here, right? So, in the case of electrophilic substitution reaction, there will be 3 steps are following. Here is the first step. One is the generation of electrophile, right? I hope you have studied in your GOC part about the electrophile, nucleophile and everything, right? So, what do you mean by electrophile? Anything which loves electrons, right? Electrophile means electron loving. So, which is having the positive charge, right? Positive charge. So, we can represent electrophile as E stands for electrophile having a positive charge, right? This is a representation of electrophile here. So, in the case of any of the electrophilic substitution reaction, the first step is that the generation of electrophile, right? Generation of electrophile. Then what is happening to the next step? These electrophile get attacked to the reactant to form a carbocation intermediate. A carbocation intermediate, right? So, this is the first step and this is the second step. Then what will happen to the last step? A carbocation intermediate is forming, right? From that carbocation intermediate, an H plus ion or a proton is removing to form the final product, right? So, removal of proton from the carbocation intermediate is the last step for the electrophilic substitution reactions. So, let us see the reactions one by one detailedly. So, here is the first step, right? Here is the first step. For example, if I am talking with the, this is Friedel-Crafts acylation, right? Okay, this is our Friedel-Crafts acylation. For example, I am taking acyl halide, right? RCOCl, acyl halide. Here our Lewis acid, right? This is our Lewis acid. What is the role of Lewis acid here? If I am taking anhydrous aluminum chloride or anhydrous FeCl3 or FeBr3, what is the role for that? This Lewis acid helps in producing the electrophile, right? Reacting with the compound. So here the Lewis acid AlCl3 react with RCOCl to form RCO plus, that is our electrophile, right? RCO plus. Then AlCl4 minus, right? AlCl4 minus. We can see by example here, if I am taking CH3COCl, right? CH3COCl, when it is reacting with anhydrous aluminum chloride, it will produce an acylium ion, right? Acylium ion. CH3CO plus AlCl4 minus. This is our electrophile generated in the case of Friedel-Crafts acylation reaction, right? If I am talking about the alkylation reaction, what will be the electrophile producing there? If I am talking about the alkylation reaction, right? Clear? If you are taking alkylation reaction, what you are observing here? We are taking alkyl halide instead of acyl halide, right? Alkyl halide react with AlCl3 to form CH3 plus. Particularly here it will form the methyl cation, right? Yes, CH3 plus plus AlCl4 minus. Then what about the halogenation? Okay, what about the halogenation here? Similarly, I am taking Cl2, right? Cl2 is our halogen. Reacting with AlCl4, AlCl3 gives Cl plus. Yes, Cl plus plus AlCl4 minus. So, in the case of Friedel-Crafts acylation, alkylation and halogenation reaction, the Lewis acid react with the components to form corresponding electrophiles. Clear? This is the first step of generation of electrophile. Then there is a special case in the case of nitration. This is a part of nitration, right? What you are observing in the case of nitration? It is treating with nitrate mixture, right? Which means the mixture of HNO3, nitric acid and sulfuric acid. So, as you can observe here, in the case of H2SO4 and HNO3, right? Okay, in the case of H2SO4 and HNO3, what you are observing here, the hydrogen atom gets released from the sulfuric acid, right? Hydrogen atom is released from the sulfuric acid, which means that in the case of nitration reaction, H2SO4 is act as an acid, right? Acid means H plus donor. So here, H2SO4 is act as an acid here. Then what about the HNO3? The H plus which releases from the H2SO4 get accepted by the HNO3 molecule, right? So HNO3 is act as a base here, right? H plus acceptor. So this reaction is an acid-base equilibrium. Acid-base equilibrium. H plus ion get released from the H2SO4, our sulfuric acid, to producing HSO4 minus plus protonated nitric acid, right? This is our protonated nitric acid. Right? Protonated nitric acid forms. In the further step, what you are observing here, right? This bond breaks, right? It will release as a water molecule, then resulting in the formation of NO2 plus, which means nitronium ion, which is our nitronium ion, which is our electrophile generated here, right? This is a special case of nitration reaction. Special case for the generation of electrophile in the case of nitration reaction. The point you have to keep in mind that in the case of nitration reaction, nitrating mixture is using, right? H2SO4 plus HNO3. In the case of H2SO4, H plus is releasing, which means that they are act as an H plus donor, act as an acid. Then what about nitric acid? The H plus which is released from the H2SO4 accepted by the nitric acid to form a base here. In general, this reaction is an acid-base equilibrium. Clear? Then what is the next step for the electrophilic substitution reactions? After the generation of electrophile, what is the next step? We need to form a carbocation intermediate, right? We need to form a carbocation intermediate. Okay. So, finally we generated our electrophile, right? In general, if you are taking any of the electrophilic substitution reaction, generally we can use it as an E plus as the electrophile, right? E plus as the electrophile, which means that E stands for electrophile and plus stands for their positive charge, electron loving. So here, this is our reactant, right? Our benzene. This electrophile get attacked to the pi bond of the benzene, right? This is one of the pi bond, right? It will get attacked to the pi bond of the benzene. So what you are observing here, this electrophile is attacking here, right? So it is observing here, a hydrogen atom is already present in the case of benzene. Then one more electrophile is attaching there. So this bond breaks, which means there is a positive charge introduces, right? Which is the carbocation forming here. This is the carbocation intermediate, right? Clear? This is a last step, and after the next step, what you are observing here right now, here this bond get delocalizes, right? Resonance, you must have an idea about the resonance stabilization. So here you are observing that these bond get delocalizes, right? Pi electrons get delocalizes, so that it will form 3 different resonance structures, right? 3 different resonance structures. This bond goes like this, then like this, like this. 3 resonance structures are forming here. Then while observing here, you can observe that this carbon, right? This carbon is our sp3 hybridized carbon, right? sp3 hybridized carbon. So if you are talking about the resonance structure, you can see that this delocalization of pi electrons happens, or it is stopped at the position of sp3 hybridized carbon, right? It will not go to the other sp3 hybridized carbon position, right? So which means that this is our resonance hybrid for the generated carbocation. We can draw the resonance stabilization here like this dotted circle, right? The circle is not completed here because there is no resonance stabilization in the case of sp3 hybridized carbon, right? So this is the resonance hybrid for the carbocation. And in case of here, this is one more name is there for this particular compound is known as sigma complex, right? Sigma complex. And as I already mentioned that there is no complete delocalization of the electrons, right? So here the aromatic structure of the complex losses, right? This is the second step for the electrophilic substitution reaction. Is that clear? Just let me know in the comments. Then only I can move to the next step. Okay, fine. So in the second step, we form the sigma complex, right? Sigma complex. Finally, it loses the aromatic nature, right? In order to retain the aromatic nature, what you are observing here, as you can see over, there is a proton is present, right? There is a hydrogen atom present in the case of resonance hybrid for the carbocation, right? So here, as you can see here, in the case of carbocation intermediate, these H plus get releases, right? Which means that a removal of proton happens from the carbocation intermediate, right? So this is our one of the resonance structure for the sigma complex. So what you are observing here, in the presence of Lewis acid compound, right? If you are taking any of the acylation, alkylation or halogenation, these are the three reactions in which Lewis acid participates, right? So after reacting with the acyl halide, alkyl halide or halogen, it will form AlCl4 minus ion, right? So in the final step, this AlCl4 minus will attack with the sigma complex to form the final product, that is the electrophile substituted product, right? Clear? Clear? Now I have a question for you. Which reaction is specifically for this particular reaction? Because it is reacting with the HSO4 minus, right? So this particular reaction is correspond to which type of electrophilic substitution reactions, as we have already seen. Nitration or sulfonation or any other reactions. Sulfonation, right? So in the case of sulfonation, when you are treating with a nitrative mixture, not about sulfonation, right? This is nitration. Sorry. Yes, if you are treating with a nitrative mixture, you will get corresponding electrophile along with HSO4 minus, right? So these HSO4 minus react with the sigma complex or the carbocation intermediate to form corresponding electrophile substituted product by release of H2SO4. Clear? So this is the mechanism for the electrophilic substitution reaction. You need to keep in mind in your examination point of view. The first step, generation of electrophile, right? As the name itself suggests that it is an electrophilic substitution reaction in which we need to produce electrophile, right? So first step, generation of electrophile. So In the case of generation of electrophile, this particular step for the nitration is very important because it is an acid-base equilibrium, right? In the second step, we need to form a carbocation intermediate, right? Carbocation intermediate. So, the electrophile get attacked to the reactant benzene to form corresponding carbocation in which aromatic nature is lost, right? Due to the delocalization of pi electron which stop at the sp3 hybridized carbon. Then finally, in order to get the aromatic nature back, these hydrogen from the sp3 hybridized carbon removes as proton, right, to form the final product of electrophile substituted product. Clear? So far we have discussed about the electrophilic substitution reaction in detail. I hope it was clear for everyone. Now let me move to the next type of reactions in the case of hydrocarbons, that is addition reactions, right? So there is a small summary about all the electrophilic substitution reactions, right? This is a substitution reaction name, their reagent, electrophile, name of the product and the structure. Clear? I hope it is clear for everyone. Keep a screenshot for this. This is the basics for the electrophilic substitution reactions for the aromatic hydrocarbons. Now let me move to the next type of reaction, that is the addition reactions, right? In the case of addition reactions, we need to focus on the hydrogenation and the chlorination, right? Hydrogenation and chlorination. So what you are observing here, same I am taking the benzene, right? First aromatic hydrocarbon, simple aromatic hydrocarbon benzene. I am treating with hydrogen, I am adding hydrogen in presence of nickel and HNO at high pressure. What I am observing? Cyclohexane, right? All the hydrogen atoms are substituted by the 6 hydrogen atoms present in the 3H2 molecule to form the cyclohexane here. This is the hydrogenation reaction. As similar to all the hydrocarbons, hydrogen always added in the presence of nickel, right? Here in the case of nickel at high pressure and HNO condition, right? High energy photon. Then what about the addition of chlorine or halogenation? Not halogenation, addition of halogen. I am adding chlorine, right? I am adding chlorine here. Benzene react with 3 molecules of Cl2. 3 molecules of Cl2. What you are observing here? Total 6 hydrogen atoms get eliminated and chlorine atoms are introducing there, right? So this will form the benzene hexachloride, BHC, benzene hexachloride. So here you need to keep in mind that if you are taking 6 molecules of Cl2 reacting with benzene, what will be the product? As we already seen in the last reaction, in the substitution reactions, right? Halogenation. What will be the product? C6Cl6, right? All the hydrogen atoms get substituted by the chlorine atom to form C6Cl6, right? So you need to keep in mind, if you are taking 3 Cl2 molecule, it will form the BHC. If you are taking 6 Cl2 molecules, it will form C6Cl6 molecule. Clear? Now let us talk about the last type of reaction in the case of aromatic hydrocarbons, that is combustion, right? As we already know what you mean by combustion. The reaction with the oxygen, right? Reaction with the oxygen. So here, if you are taking benzene, right? If you are taking benzene, and there is a small equation to keep in mind. Right? This is the general equation for the combustion for any of the aromatic hydrocarbons. For example, if you are taking CH6, right? If you are taking C6H6 instead of here, you will get an combustion product like this, C6H6 plus 15 by 2 O2 gives 6 CO2 plus 3 H2O plus heat, which means it is an exothermic reaction, right? Heat releases, which means it is an exothermic reaction. So based on this particular equation, you will get the combustion reaction for any of the aromatic hydrocarbons. Clear? Okay, this is the last part of the hydrocarbons chapter. That's why I'm going to the concept only here. If you want, I will be coming back with the PYQs with the same chapter. If you really want, I will come back with the MCQs, right? So that's all about the chemical properties of aromatic hydrocarbons. Now let us talk about some different properties, right? Directive nature. Directive influence of the functional groups in the monosubstituted benzene, right? For example, if I am taking benzene substituted by the CH3 molecule, right? If I am taking toluene molecule, I will write here. If I am treating this particular toluene molecule with any of the reactant, right? For example, if I am taking with right? If I am taking toluene molecule here, what will be our product? It will depends on the directive influence of the existing functional group here, right? In the case of toluene molecule, what is the existing functional group here? What is the existing functional group here in the case of toluene? CH3, right? Our methyl group is the functional group which is present in the toluene molecule. So this will decide this chlorine will go to which of the position, right? Which of the position. That is known as the directive influence of the functional group in the case of monosubstituted benzene, right? So as we are discussing about the isomerism of aromatic hydrocarbons, Kunal Patil, which point I want to repeat? This point, right? So if you are taking any of the monosubstituted benzene, right? Monosubstituted benzene. For example, if I am taking any of the X stands for any of the functional group, right? So this functional group, we are not getting the lecture because of language. Okay, after this session, just go through the NCERT textbook, then watch the recorded session again, then you will get an idea, right? So here, if you are taking any of the substitution, right, any of the substitution like X here, this will decide the next group will attack to which position, right? When we are discussing about the isomerism of aromatic hydrocarbons, we have seen that ortho, meta and para position, right? 1, 2, 1, 5, 1, 4, 1, 6 and position, right? So here for example, if I am taking phenol molecule, right? Phenol molecule, this is our phenol molecule. I hope all must have idea about to write down the resonance structures, right? Resonance structure. Okay, daily we have the lecture time at 5 to 6 for chemistry, 6 to 7 for maths and 7 to 8 for physics. Right? So try to be participate in the daily session, right? It will be helpful for you. So here, right, OH molecule. While writing the resonance structures for this phenol molecule, you can see that this is our electron density, right? This is our electron density. So here, this electron density will be present at these positions, right? What are these positions? If I am taking, this is the first carbon, right? First carbon. This is second position, right? So this is the first carbon. This is the second position, right? Second position. Then what about here? 1, 2, 3, 4. Fourth position, right? Then here it is fifth position, right? So here 1, 2 position or 1, 5 position is known as ortho position, right? We have already seen the last class. Right? Yes. So here 1, 2 and 1, 5 positions are ortho position, right? What about 1, 4 position? 1, 4 position of the benzene ring. Para position, right? Para compound or para position. So we can say that here the electron density is present in the ortho and para groups, right? Ortho and para position. So we can say that this OH will direct the other incoming functional group to the ortho or para positions, right? Ortho or para position. So we can call these particular compound as an ortho para directing group, right? Ortho and para directing group. Is that clear? Just let me know. Is that clear? Okay, hope it is clear for everyone. Similarly, hi Rana. Similarly, if you are taking NH2 group, right? NH2, NHR, NHCO-CH3 and OCH3 group, both of them when you are writing about the resonance structure, you can see that the electron density is maximum at the ortho and para positions, right? So these functional groups will direct the incoming functional group, incoming group into the ortho or para position. So they are known as activating groups or ortho para directing groups, right? This is the example for that. This is our phenol molecule. If you are adding 3Br2 molecule, right? 3Br2 molecule. As you can see over here, sorry, there is a small mistake. This is sixth position, right? This is the sixth position. So here 1, 2, 1, 6, 1, 4, which means ortho para directing group, right? Ortho para directing group. Then what is the other possibility? So if you are taking NO2 molecules, right, NO2, groups like NO2, what you are observing here, if I am taking nitrobenzene, then I am treating with nitrating mixture, right? I am doing nitration of nitrobenzene. 3 different products are observing, right? This is our 1,3 position, right? What do you call as 1,3 position compounds? What will you call for the 1,3 position of compounds? Meta groups, right? This is meta. Then what about here? 1,2. 1,2 or 1,6, it is ortho, right? Then 1,4, right? This is para group. So, in experimentally it is shown that meta compound will be formed in the major, which is about 93%, right? 93%. So, we can say that according to the resonance structure, right? According to the resonance structure here, what you are observing here, if you are talking about the electron density, again here you can say that all the electron density is maximum in the case of meta position, right? Meta position in the case of NO2 groups. So, which means that these NO2 groups will direct the incoming group to the meta position, right? Which means 1,3 positions. Clear? One-three positions, right? So similarly, if you are taking NO2, nitrogen, carboxylic acid group, right? C double bond OH, COR, C double bond OR, CHO, aldehyde, SO3H, and all the halogens, it will be meta directing group, right? Clear? Rana, no need to worry for the less marks in the JEE Mains. You have another exam for the private engineering college exams also, right? So no need to worry. So we will be moving to the last part of aromatic hydrocarbons here. That is about the carcinogenicity and toxicity, right? Carcinogenicity and toxicity. What do you mean by carcinogenicity? If any of the compounds which result in the cancer, right? Which are causing cancer is known as carcinogenic compounds. Yes. Meta position means, so here, right? For example, if I am taking this molecule, right? Okay. If I am taking this molecule, 1, 2, 3 position, right? I am starting numbering from the first CH3 molecule here. So this will be 1, 2, and 3, right? This will be 4th position. This will be 5th position, right? And last one, it is 6th position. In order to based on the position of the different groups, we can say that 1, 2 positions are known as ortho position, right? Okay, 1, 2 position means it is ortho position. 1, 6 is also ortho position, right? If you are taking 1, 3 or 1, 5 position, it is known as meta position, right? Meta position. If you are taking 1, 4 position, it is known as para position. If you are not clear about this thing, just watch the recorded session for the last class about the aromatic hydrocarbons, right? Just recorded yesterday. You can go through our channel, watch the particular section. Then you will get a more idea about the ortho, meta and para positions, right? Okay, our studio is in Hyderabad. The lectures are starting from the Hyderabad studio only. Here, we are taking session from the Hyderabad. Okay, now let us talk about the carcinogenicity, right? If you are taking any of the polynuclear hydrocarbon, benzene and polynuclear hydrocarbons containing more than 2 benzene rings, which fused together, they will act as a toxic compound, right? They will act as a toxic compound here. So they will cause cancer. That is why they are known as carcinogenic property. So such polynuclear hydrocarbons formed on the incomplete combustion, right? Incomplete combustion, like if you are taking tobacco, petroleum or something, if they are undergoing the incomplete combustion, they will form the carcinogenic product, right? Right? So there are some examples for that. First example, it is 1,2-benzanthracene, right? 1,2-benzanthracene. Again, more benzene rings are present, right? So when you are entering in your human body, it will causes cancer. And another example is 3-methylchloranthrene, right? 3-methylchloranthrene. Then 1,2-benzpyrene. And last one, 1,2,5,6-dibenzanthracene. And last one, 9,10-dimethyl 1,2-benzanthracene. These are the structures which is given in your NCERT textbook. W, your question is about NO2 group, right? NO2 is ortho or meta, ortho para directing or meta directing, right? Okay, which one is wrong here? One three position, right? Actually, I didn't get your question. If you're talking about here, you can see that this is 1,3 position, right? So this is a meta compound. So in general, NO2, if you're drawing about the resonance structures, you can see that the electron density is maximum here at the meta position, right? Yes, meta position. So we can say that this NO2 group will direct the another compound, another group into the meta positions only. So this is generally meta directing groups. Okay, here in the case of nitrogen, right? Just think about that if you try to write down the resonance structures for the nitrogen compound, right? What you are observing, whether it is ortho para directing or meta directing. Just think about that. Clear? Okay, in this percentile booster batch, Pratnya ma'am is taking the math classes from 6 to 7. Right, that's all about from my side for today. We have discussed about the physical properties, chemical properties and the directive influence of the functional groups, right? Then finally we will talking about the carcinogenicity and toxicity, right? Okay, you are saying like that nitrogen is ortho directing, right? Okay, fine. Let's see. Okay, so far we have successfully completed our hydrocarbons chapter here, and there is a gentle reminder about the AATS for JEE Advanced 2025. Limited offer is there, so you can enroll fast now. So finally JEE Main exams are over, right? So you must have idea about your score, right? If you are entering your score in your college predictor, you will get an idea about the list of different colleges according to your score, right? So link will be provided in the description, you can check now. Just enter your score, you will get a list of different NITs, IITs and colleges, right? Then finally, if you are not getting any good rank in the JEE Main exam, no need to worry, there is another option for that. So many private engineering exams are there, right? Like this, so you will get an opportunity from the Infinity Learn side. A test series is providing there, so you can use 70% off code to get in. Best 70 off code to get in 70% off for this particular series. So enroll fast, don't miss this opportunity. Okay, so that's all from my side for today. I hope it was clear for everyone. If you guys really enjoyed the session, hit the like button. Share this particular session to your friends. Or if you have any doubt, you can ask, otherwise we can wind up the session for today. So don't forget to subscribe our channel, Infinity Learn JEE YouTube channel. And these notes will be provided in our Telegram channel, Infinity Learn JEE Telegram channel. So just join our channel to get the session notes after every session. Okay, till then, bye-bye all of you. Tomorrow I will be coming back with another chapter in the grade 12. It's about the solutions chapter. So till then, bye-bye. Take care.
Also do like find AC, DC, DC,